In the chemistry textbooks, there's a section on vapor pressure, and some students have a sense of what it's all about, some don't. There's also a section on heat of vaporization and rates of evaporation, etc. And I've always looked for demonstrations that kind of illustrate that and get kids a little bit more involved. I saw this the first time, I believe, at an NSTA convention in Dallas. And the initial way I saw it done, students stood up on top of a demo desk and poured liquids out of one beaker down to another beaker on the floor, and they called it the splatter test. I'm still calling it the splatter test. I've simplified it a little bit. It still involves throwing some liquid, which in some cases might bother you a little bit because throwing chemicals is a problem occasionally, but I find it to be a really nice illustration of evaporation rates and vapor pressure. So I still like to use it, and I also like to use it because it gets a number of students involved in the process. So I have chosen 3 volunteers who have graciously accepted to volunteer, and they're coming out now. And I'm going to give each one of them a small, carefully measured quantity of liquid. And believe it or not, these actually were carefully measured. Not by me, but by someone else. Unfortunately, I'm not going to use the amount that's in there. And so the first one says acetone, and I'm going to hand you the acetone beaker. Well, you want to go this way? We're going in? Okay. All right. Tell me what to do. That's good. All right. So we're going to go the acetone beaker. And the next one is water. Wow, this is the water one. So here's water. Another carefully measured quantity. That's exactly the same amount that I've given in acetone. Don't look at it. Jeez, acetone. Okay, and this is ethanol or grain alcohol. Another carefully measured quantity. We'll set that over there. Okay, now, what I'd like you guys to do is come over here in front of the chalkboard and line up right across here. Stand in front of the circle that is your particular liquid. So I think we've got this. And this is acetone, water, and alcohol. So we're in good shape. Now, in a moment, I'm going to ask you to simultaneously, all at the same time even, throw your liquid at the circle. And as you all are completely aware, I'm sure that's throw the liquid, not the beaker. So you will, at some point, hold on to the beaker and let the liquid fly towards it. We're trying to hit the center of the circle. Once you've released it and it's hit the center of the circle, really we need to move off because we want to make observations. And in fact, your classmates are going to be carefully observing what you have done and make some interesting observations about what happens in the process. Okay, so are you ready? All right, so on 3, we'll have you toss the liquid at the circle. And then again, move out of the way so we can watch the evaporation process taking place or check the phenomena. All right, are you ready? Okay, 1, liquid, not beaker. 2, liquid, not beaker. At the board, not at the teacher. 3. Oh, these guys are good. Wow. At this point, I would get, thank you, by the way. How about a hand for these guys? They did a nice job. This, I've probably done this thing 400 or 500 times, and with the exception of a little bit of liquid over here on the wall, I don't really see much anywhere else other than the wall and a touch on the floor there, which is really nicely done. I mean, a lot of times it's on the back wall and various other things, but already I think you can see some things that are going on. What I would hope that my students focus on is, hey, the acetone, it's already gone. The alcohol is not quite gone. And the water, is still pretty well there. There's some other really interesting things that students pick up on here too, though. Notice what the water did. It was thrown, and look what happened. Almost all of it stayed together. Hit in a clump, and then after it hit, it went down the board in pretty tight rivulets. It stuck together pretty well. The acetone It's all over the place. There's dots over here, there's dots down there, there's dots. It spread out almost like a shotgun effect as soon as it took off. The alcohol, kind of in between. The alcohol, didn't come out quite all together, but it did spread out a lot more. And notice how it went down the board. It didn't go down the board in nice little rivulets sticking together, but instead kind of spread out over the surface of the board. All of these things are indications that the water molecules did the best job of sticking together, the acetone molecules did the worst job, and the alcohol was kind of in between. So at this point, maybe all you're trying to illustrate here is rate of evaporation. Some liquids evaporate faster than others. Acetone evaporates faster than water and alcohol. Alcohol evaporates faster than water. That may be where I want to stop. If all I'm talking about is volatility of liquids, I'm done. If I want to get into it a little bit more, now I'm going to start talking about the molecules that I'm working with. And we've got over here Lewis dot structures. That's my Uncle Gilbert, by the way. Gilbert Newton Lewis. We called him Newt in the family, but you probably knew that. Water molecule looks like this. Acetone molecule here. Ethanol molecule here. And at this point, I probably jump into the different types of bonding between the molecules. Water and ethanol have a hydrogen bonded to an oxygen. Hydrogen bonding exists in water molecules, it exists in ethanol. In the water molecule, the hydrogen bonding is considerably stronger because you don't have this carbon into the molecule as you have here in the ethanol. In the water molecule, we've just got the hydrogen so they can bond to other oxygens and continue to bond out. That gives you a lot stronger attractive force for water. Ethanol a little bit lower because there's not much hydrogen bonding on this side. And with acetone, there's no hydrogen bonding. The hydrogens that are there are hooked to carbons. That doesn't give you hydrogen bonding. Hydrogen bonding only occurs with oxygen, fluorine, and nitrogen. So it's nice to look at the structure this way. I'm going to move back over to the table briefly. The other way to look at it, and I think maybe even better, perhaps, is to look at the models for the three molecules, and again, look at the structures of them. The water molecule here, the bent shape associated with water. And if you look at the similarity, here's what happens with ethanol. You replace that one hydrogen with two carbons. A little bit bigger molecule, a little bit less hydrogen bonding on this end of the molecule, so ethanol, alcohol, has a weaker attractive force. Then you go to acetone. There are no hydrogens bonded directly to the oxygen. There's no hydrogen bonding at all taking place here in acetone. You can go farther with this if you want to, or you can stop at this point. This is really where I quit with it. At this point in my class, the only other thing I might just point out is that when you start talking about properties for water, and you're illustrating this to your students, and you say, okay, if you see a test question and it says water surface tension is high because of, if you see something about vapor pressure and you want to explain why water has an unusual property, 9 times out of 10, the answer is hydrogen bonding. Most of the properties that we think of that are unique about water and interesting about water, whether we talk about its expanding when it freezes or its surface tension or anything else, the answer is almost always hydrogen bonding. And many of our unusual properties for liquids in general are related to hydrogen bonding. Here's a nice way to look at it initially in terms of structure. This is a fun way to get into it. It's also a fun way to get some kids involved in an experiment where they're throwing stuff on the board. It's a little kind of a non-traditional thing to do.